but lots of biomedical applications as well. We will learn how the inhaler works, especially the current inhaler devices, how do these work. So my plan is first to show you how inhaler works, and then how that inhaler can be modeled within CFD, and how CFD can be used to optimize the inhaler, how you can design a new inhaler, how you can optimize the performance of inhaler, how can you make a smart inhaler. So all these things you can do after carrying out the simulation. So let us see this. The inhaler that we are having is Respiclick ventricular inhaler. Before I start my discussion on this, let's have a look at how it works. So I've got a YouTube clip on that shows how it works, so that you can have a physical feeling of that. Mouse problem. शुक्ला जी, दो मिनट का ही काम।
This video is designed to show how the ProAir works. Albuterol sulfate inhalation powder inhaler works. It's not intended to be instructions for use. Please see the patient instructions for use and the accompanying full prescribing information. Hold the inhaler upright. When you open the red cap, you'll hear and you may feel the click.
So look at the inhaler, how it works.
After you breathe in your nose and close the red cap, this pushes back the spring at the top, allowing the air pump to expand and resets the mechanism. So you're ready to load another dose whenever you need it. When you close it, you'll see on the back that the cap moves down to show that the dose has been prepared and also to indicate how many
कोई दूसरा माउस है क्या? Do you have different mouse?
now that you know how it works. At ProAir.com/.
Right, so you have seen here now here, this part. What you can see here is a meter dose has come from here, in here, and there are two inlets, and there are three blades here. So what happens is, when you press the material which comes down through this, because of a rotation imparted here, there is a vigorous mixing between air and the powder that has come out, and then that can be discharged through this particular duct. So this is where the mixing action takes place, and we would like to have maximized mixing here. So for example, how big should be our air inlet ducts, because air comes from here and here. So these are the air inlet ducts. What should be the dimension of this for proper mixing? We have blades here. What should be the dimension of blades? This is the part through which the powder with air is inhaled. How this should be designed, because you will see that later the deposition can take place on this discharge duct. So from mechanical engineering point of view, a lot more can be done to design this. So in this particular class we'll see how this model can be designed basically in CFD, how we can see the performance of this device using CFD, and then later on, if you wish, like those who are doing masters or BEng and all that, you can take a project on that, on designing an inhaler. So unlike the previous cases, we don't have arteries, we don't have stents, we are working on a mechanical device on a product development phase and how it works. This is already commercially available. So we have taken, for example, a commercial device that we would like to analyze using CFD. Okay, this is not a sponsored work. We just took it from the commercial models available, because they are available in the market. So we are just trying to develop a model and see how it works. Right, so we have learned about the device. So as I was mentioning, it's known as ProAir Respiclick VID inhalation driven multi-dose inhalation powder device. So the inhalation powder, which is albuterol, known as salbutamol, is used to prevent and treat wheezing and shortness of breath. It's very commonly used for a variety of applications. The advantage of the way it is being created is that you can have a exactly metered dose. You can exactly meter the dose. So when you press from the top, the spring, a given amount of dose comes down, which mixes with air, and you can deliver it. So unlike the previous cases where, depending upon how many times you press, you get the amount of medicine in your system, here you can have actually metered dose. Now, although it is also not, I would say it can still be improved in many ways. We can have smart systems where, depending upon your breathing ability, the amount of drug that can be disposed of in your mouth can be varied depending upon your breathing ability. So there are systems where initially you use the inhaler to give an idea about your breathing capacity, and once your breathing capacity is known, then a proper amount of the material can come. And in old age, breathing capacity decreases. For young body, breathing capacity is much stronger. People who are ill have less breathing capacity. So we would like to put enough material, enough drug inside the body that is required for the treatment. Now if that is dictated by how much we can breathe in, then there is a problem, because if my breathing ability is very low, most of the drug will be in my mouth cavity. It will not go, it will not reach where it should. So how do we do that? Lots of work is being carried out here. This is the first stage in which we have done some work on carrying out the flow analysis within the inhaler, and then by varying the dimensions of the inhaler, we can see how good or bad the mixing is. So this is the ProAir VID. What we are doing here is, again, we will do CFD simulation of this device. You can go to the market and you can look at this device. We will create a geometry which is representative of that VID. A mesh will be created, we will solve governing equations, and then we will have solver settings. In this case, CFD bit is a bit more involved than what we have done in earlier. Like when you remember, we did arterial bifurcation. This was a straight line flow with bifurcations. Equations were simpler. Even when we did VAD, ventricular assist device, things were rotating. Okay, so we had one interface at the inlet and outlet, and things were rotating. Then we went to stent, where we put stent inside the straight pipeline artery or carotid bifurcation. This is a bit more complex, because what we'll do is we will have a device, we'll model the device, and then we'll track the particles that are injected inside. So not only we have to run CFD flow simulation, we have to run discrete particle model as well, where discrete particles are injected into the flow and that passes through the flow, and we can see how that flow is taking place. So this is slightly more involved model. Now if you look at the flow part of that video that I showed you initially, you saw how the air was coming from here and it was getting mixed here. So we have created a representative model of the same thing. What we are going to do is, we are going to create this mixing chamber, we are going to create the blades. I have been saying blood too often, so that's why blood is coming, but we should create blades, and we should allow the material to be injected from here. So material is being injected here, air is coming from here, the mixture is being formed here, and then this mixture is transmitted across it. So in today's class, we'll try to see how this thing can be modeled. This is a fairly good representation of the actual system. The type of models we'll do is, first we will run a steady state, nothing is varying with respect to time. We will use multiple reference frame model, where we are talking about the revolution average values of this. The second thing will be, we will use MRF and discrete phase modeling. So we got the MRF work, but then we'll inject particles from here and see how these particles mix as they come out. The third thing will be transient condition using sliding mesh technique and discrete phase modeling. Here what we'll do is, we will rotate the blade, actual rotation, not as the approximate rotation using MRF, actual rotation, and we'll see as it rotates how the particles get mixed and how the particles come out of it. Okay, so this is the 3 steps. It's slightly more involved step, and I'll demonstrate it to you here how these things are modeled and how do we get results. So initially simulation will run at a steady state to stabilize the flow. As you can see, things are moving a bit, so flow simulations may not be right. And once the convergence has taken place, we will use sliding mesh technique, where we will move this part and see how the at each degree of revolution, how the simulation, how the flow is developing, and how this motion of the particles is taking place with the system. Okay, any questions on this? Do you think that this is an accurate representation of the inhaler device? You happy with this? No? Happy? You always seem happy. Good. So this is how the inhaler device is being created, and we will see how it can be generated. Again, the philosophy here, how should we do it? We have to create this cone, we have to create this cylinder, we have to create this inlet and outlet, and we have to create this outer duct. So these things have to be done. If you are CAD expert, or even you know a bit of CAD, how can we do that? So you can see here, this is symmetric along this line, isn't it? Symmetric along this line. So what we can do is, here we can create a sketch and revolve half. Then we can create a sketch here and revolve. Then we can create a sketch here and extrude. We can create a sketch here and extrude. We can create a line here, a sketch, and we can sweep along this. So very simple, 3-4 steps we can create the geometry. The complications is in creating blades, so we can create a sketch, extrude, and then create the blade. Then we can pattern it around it. So we can have 3 blades here, and then we can create the cylinder. So this is the philosophy. I'll explain to you step by step, and then I'll show you video of this creation so that you have better idea of this. So there are several stages that have been formed, that I have used here, as I mentioned to you. The boundary conditions that I'm going to use here at a steady state. The inlet 1 and inlet 2 are these 2 inlets. This is inlet 1, this is inlet 2. From both these, an assumed velocity of 0.5 meters per second has been taken. Outlet pressure has been taken to be the 0 pressure gauge. So here at outlet, I am assuming 0 pressure. As I mentioned to you earlier, actual pressure load doesn't matter. It is the pressure difference that matters. So So here it is 0 pressure. Material is air and model is turbulent. So we are assuming flow to be turbulent. In the second case, when we run DPM, we use the same settings, but for discrete phase model, DPM is discrete phase model. For DPM, we are using the material salbutamol, where I am selecting these particles. These are taken from reference 0.0032 millimeter, and I am injecting it for 0.04 seconds. And velocity magnitude that is coming is 11.3 meters per second. This is velocity of the particles coming out. The boundary conditions at unsteady state, again, when we are running the sliding mesh, we are using this, and for the discrete phase model, we are keeping it same. We are keeping the material properties same, the exit velocity of the material same. So these two are the discrete phase models. In CFD, first we execute this, and then on this flow field, we execute this. So it is like this. First you run the flow, only air flow is simulated, and then you inject particles. So the particles are affected by the flow field around it. So you get the particle tracks. Okay. Now there are various ways of doing it, which is known as Eulerian-Lagrangian model. So Eulerian model you run first, and then you run the Lagrangian model for particle motion. In the second case, you run it in interactively. So Eulerian, Lagrangian, Eulerian. So you can consider the interaction of the two. So these two types of models can be run. Right. So I'm coming to geometry creation. As I mentioned to you, straightforward. I'll go through it reasonably quickly, but then I'll show you the video where it is exactly how it is created will be shown to you. Here I'll give you just the overview of that. Okay. So we create the inhaler folder. Straightforward. Open ANSYS. Go to this pad, then save this project as inhaler CFD project. Click on geometry, create the plane, open the display plane box. This is where we start every day, and today also we are starting from here. We change units to millimeter, and now things start. So first thing we do is we go to XY plane. As I mentioned to you, first thing we are doing is we are creating the cone. Okay, we are creating the cone at the bottom. So how do we create? It's very simple exercise. We go to XY plane and create this sketch. So you can see this is sketch I have created. And in this sketch, we are giving dimensions 6 millimeters for H3, 30 millimeter for H6. So all these things you can see, H3, H6, this angle you can see which is 60 degrees, V2, V5, 10, 15 millimeters. So all these dimensions we give. So then this sketch is created. So you will be having this sketch here. This is V1, V2, A1, H8, sorry H3, and then you have H8. This is H6, this is H8. So this is what you have created there. So this sketch is created. Okay. Now this is your vertical axis. This is your vertical axis here. Once this sketch is created, it's very simple, straightforward. We go to revolve. Okay. As we go to revolve, then the revolution, we go to revolve here. And in revolve, then here in geometry, we apply sketch 1. We select sketch 1 and apply here. Axis is 2D edge. We create direction to be normal and we revolve it around by 360 degrees. We press it generate and this is created. No problems at all here. You have the conical part and part of the upper section formed here. Okay. Now because this part is hollow, there will be a hollow part here, isn't it? It will be a hollow cylinder here, and you have the central part which acts like complete flow domain here. This will be complete flow domain, but here you have this hollow part on the cylinder. Is it clear to everyone? Sketching it is very easy. Only thing is we have revolved it. Then what we are doing is, we are creating a new plane. So we go to XY plane and we hide this sketch now. So what we are doing is, we have hidden the sketch that we have revolved, that made it, and then we create another sketch from this face. From this face we create another sketch, and this sketch is one line here, one line here, and an arc here. So we create a straight line of dimension, then we create another line, and we join these 3 points by an arc. So we have arc. Arc has got, if you go here, this angle is 105 degrees. This is V15, that is 8 millimeters. So this is 8 millimeters. R16 is 10 millimeter, and H17 is 35 millimeters. So we create this line, this arc, and this line. Why are we doing it? Again, we want to create the outer duct, and this has been done from an actual physical model. This is not from any reference or something. We had one inhaler device, we measured everything, and then that's how we are creating it. So how can we create the outer duct now? We can create outer duct by having a plane surface here and sweeping it across this. Okay, so we go to the sweep model. Any questions at this point, please? You all are reasonably comfortable in CAD, so any question on this? So after this, what we do is, we click sweep and we sweep this surface across this, and we use add material option and we generate it. So then this part is created. Okay, this part is created. So you have the lower lower conical duct alongside the diffusing duct, which you put in your mouth when you are inhaling it. Okay. Any questions, please? Any questions? Now, what we are trying to do is, we are trying to create blades inside and and the inhalation cylinder inside. So we have to create some surfaces, because the middle part will rotate, outer part will remain stationary. So I have to create another surface here. There is one surface here already. I have to create another surface, one which remains stationary, one which rotates. Likewise here, one surface will remain stationary, other will rotate. So we create a sketch on the same plane again of this nature, and the dimensions of this sketch are given here. So we create a sketch, this and this, and then we will revolve it around the center point, so that we can create other parts of the system. So we create this sketch. Dimensions are 27, 22, 4 and 10. So these are the dimensions created here, and then we revolve it. Only one thing we have to do different is that we have to have add frozen. If we didn't have add frozen, it will be merged into it. By add frozen, you can have that entity separate from the existing model. If you had used add material, it will become part of that. So we used add frozen. So this part is separate now. This part is separate to this part, and as you can see from the color, this is slightly darker gray, this is lighter gray. So these two are two different parts within the same system. So we have modeled this inner part and the outer part. Now next bit is, in the inner part, how do we create the rotation and the cylinder? Any problem here up to this particular point? Any of you? Suppose if your life depended on it, you can create it in 15 minutes? 5 minutes even. So this is created. Now let us go to the next step. Now what we are doing is, we are creating blades now. So again we go to the, we hide that sketch, and now we go to ZX plane, because now we are creating blade on top. So in place of XY plane, we go to XZ plane, top plane. And when you look from top, this looks like this. So what we are doing now here is, we are creating blades. How are we creating blades? So we create a rectangle first, the inner circle is already created from the previous sketch. The inner circle is created. So we create another circle here, and why are we cutting circles? So that we can create curves here, and then we cut all these parts from there. So you can see here, we create a rectangular sketch. We use this as the axis of symmetry, that's that we have exactly symmetrical blade here, and then we create a bigger circle here, and we use this bigger circle to create a curve here, and that we do by cutting all these surfaces from here, as you can see, and then we use this dimension so that it perfectly matches with the inner cylinder. Okay, is it making sense? So what we have done, created a rectangle. This is the inner circle. So we create a slightly bigger circle. We cut this part and use these dimensions such that it smoothly matches with the cylinder there, because this part is going to rotate. Okay, cylinder will not rotate, but blade is going to rotate, so it has to match flush with this particular part. And then we extrude it by 5 millimeter. So we choose that sketch, add frozen, and we sketch it up by 5 millimeter. So then your blade is created. Your blade, which is flush with the cylinder, is created. Okay, we press generate. Any questions on this, please? Okay, so this is the blade creation, very simple part. After blade is created, we create a pattern, very simple pattern. We create two more bodies. So here we are copying 2 and along this normal place, and it is evenly spaced. So if we go to the ZX plane, we create pattern, and in pattern we create pattern for this for 2 more blades exactly like this. So then we can generate, and we can have 3 blades inside the system for a normal inhaler. So this way we can create the patterns and the blades are created. Okay, any questions, please? So this way at least we have simulated the inner part of the inhaler. Okay, like when you see a commercial product, you may feel that it's very easy, but to create that it can be quite challenging. So this is generated, and now because this is a solid part that rotates, we have to subtract this blade from the flow domain. Okay, so what we are doing here is we are going for Boolean operation, and we are subtracting this blade from the flow domain, because these blades are going to rotate. This is solid body. Okay, we are not going to solve our flow equations on the blade. Flow equation is to be solved between the blade. So that is why we need to subtract these blades from this. So we subtract the blade. So we have a void there which acts like a solid, and flow simulations are only solved in between the blades and not on the blades. Okay, so that way we can get that effect. Keep in mind, this entire part will be rotated. This entire part will be rotated because this is the part that rotates in that particular cylinder. And now once this part is taken care of, I have to create injection mechanism. Now how am I creating injection mechanism? By creating a cylinder here and using this surface as the injection surface, like when you press the inhaler, the fluid comes from this. So this is your injection surface, and the powder will come from here, air will come from the sides, and then it will mix delivered here. So what we are doing here is we are creating the cylinder. So we go to primitives, we go to create, toolbar, primitive, and we create a cylinder here of a certain dimension which is slightly more than the blade dimension outside.
Sir, what is the material which will be combined with the air, then it will get to our
Subitumol, no? We mentioned that. Did not hear it? Hmm? Did we not mention that? Here. Salbutamol, isn't it? This is the material. Powder. So the diameter is 0.0032 millimeters. Okay, so this is coming from the injection surface. So we created the cylinder for injection, and we simplify we crop the extended lines and arcs, so anything that was outside it is removed, so that the surfaces that are created are perfectly smooth, and they represent the real picture. The dimensions that we will use for this is, these are the dimensions that we'll provide. Now, one thing now we have to do is, which is important, is to create the inlet duct and outlet duct. Okay, sorry, the inlet ducts, basically inlet duct 1 and inlet duct 2. The way I am thinking of doing is that this is your ZX plane from the top surface. If I create an inlet duct here, so we create a sketch, extrude it on this direction, create a sketch, extrude it in this direction, isn't it? Then you can have two inlet ducts. So that is why this surface is created. Likewise, this sketch is created, and then if you give these dimensions, they will be flush with this surface and this surface. So these dimensions have been selected that they are completely flush with the outer cylinder, okay, that it matches with the outer cylinder flush. What we'll do is we will extrude them. So this is what is created by giving those dimensions. We extrude it down and use add material. Because we are using add material, it will fuse with it, it will combine with this with it. So this way you have created the two inlet ducts, this one and this one. So air can come from here as this rotates, as this is rotating. Okay? Any questions on this? That is the design modeler part. Was it difficult? Why? They are the easiest one. You just create the sketch. Because actual system is like this. We are trying to create the real system. As I said, this is the real system, but you can modify it. Obviously, you can change the dimensions, you can modify the shape and all that. Probably this is the work that you can do in your time. But this is, we are mimicking a real system. They have done it, so there must be some reason behind why they have done it. This is properly, your question is right, but this is purely direct the flow in a tangential direction. We just have a hole there, tangential. They have made it, so air comes in here and it will be smoothly taken in this direction. Okay? Same thing here, this is also coming tangentially. They want to increase swirl, and because of swirl, mixing can be increased. So everything has got a reason why they have done it like this. Okay? Any more questions on this? Yeah. The real system has two inlets. Real system has two inlets. So you can have it, but like suppose from your point of view, if you are a production engineer and you have to approve the design, how many inlets will you go for as a manufacturing engineer? One thing is academic exercise, second thing is requirement. So typically two coming from the two sides will give enough air. Now if it is so we want more and more air, then probably we need more inlets, because this is very, very small dimension. So two inlets will be more than enough, isn't it? But if suppose it's very big, you may go for, if your air requirement is more, you can put more inlets. In this case, this is the real model, actual model that they manufacture. Okay. Right. So this part is done, and now we can go to create mesh part, which is slightly complicated in this case, but the geometry is created, and I am reasonably satisfied, and I hope you are, that this is a real replica of the actual system. Okay. Now I must mention to you here, I think if you should keep in mind, that even the sliding mesh may not be actual representation of the flow. So CFD that we use, it is intended to be 100% of the actual system. We will try to be as close to the system as possible. Many people say that MRF is good enough representation from industrial point of view. That is, I agree with that. MRF works reasonably well, but it doesn't give us enough information about the flow field. Why? Because you get revolution average values, where things change at every minute. Now in sliding mesh, the problem is we are rotating this entire zone at constant velocity. In reality, only blades are rotating, aren't they? In reality, only blades are rotating, and there may be a velocity gradient in this direction, But in FD, we are rotating the entire part. So that is again a simplification. But in this case, error will be far less. Error will be far less. At least this entire part is rotating. So those who are working on CFD and feel that I have done sliding mesh, it should match experimental data. There are still inaccuracies here. Okay, so this thing you should keep in mind. This is as close to the possible To get actual flow condition, you have to use dynamic mesh. Okay, dynamic mesh only where you rotate these blades. You don't.
But dynamic mesh will take more time and more computational problems.
So
We have to be
yeah, so the thing is, good things don't come easily, do they? So are you going for good, or are you going for just good enough? Good enough, MRF is okay. Reasonably good, sliding mesh is okay. Very, very good and accurate, you have to have dynamic mesh. But the problem is in dynamic mesh you need very fast computers and it will take a lot of time. Sliding mesh is a good approximation in the middle. MRF can be fast, still there you need computing power. But as a CFD, because if you happen to work in this particular area, you should keep that the CFD simulations are the, we're trying to create real life situations to as much accuracy as possible, given the resources that we have. But if you suppose don't have enough resources, we will do MRF. In this case, we are using sliding mesh. Okay, but to run dynamic mesh, you need more information. Then you have to give moment of inertia of all these, because then you are modeling the motion dynamics of the inhaler as well. So it becomes more complicated. It will be a bit more difficult in that particular point of view. Okay. So can we move to mesh? All of you? So mesh generation. So we will now go to the mesh generation, and we will get it here. If you click on the geometry part, you will notice that we have named solid. So it is better that we name it appropriately, that we can identify later which solid is which. So we are renaming them solid. The first solid is the outlet domain, the second solid is the cyclone separator, and the third solid is the inlet domain. So we have the three bodies, we name them. Just go there, right click, and then you can rename them as you want them to be renamed. Okay, as you want them to be named, just for that it is easier for you later on to analyze it. The next thing is naming convention. So what we do is we name the inlets, as I mentioned to you. Left click and then right click, go to named, create named selection, give inlet 1 to one and inlet 2 to the other, as we have done in the past. Inlet 1 and inlet 2, two edges, inlet 1 and inlet 2 done. Then this is the injection surface, so we name it as injection surface. So this is injection is coming from there, coming through a straight line and then diffusing into the outlet. Okay, so it will come from here, get it mixed here and go out. This is your outlet, so name it as outlet. Then from the top, this is the interface with the outer domain. So this is a stationary part. Now we use interfaces, I have explained to you earlier, we use interfaces when we have to transfer data from one plane to the other. So for example, this is the bottom face, this is the top face, these two are same, isn't it? but this face is rotating with the rotating part, and this face is stationary. So when you are solving the equations, you are solving equations here and here. Okay, you are solving equations which is on the stationary part, you are solving the equation in the moving part. Same Navier-Stokes equations. How will you transfer data from moving part to the stationary part? So for that, what we do, we create interfaces. So on interfaces, what happens? We are doing simulations at the top. So we calculate the values, and these values are identically transferred at the node points on the same interface. Okay. So this is the way how motions are being modeled in CFD. The top bit is rotating. We are calculating the values. This value is transferred at every time instant onto the lower interface. Okay, making sense? All of you, really? Lady at the back, is it making sense? Is it making sense what interface does? I'm not picking on you, so don't worry. I'm not trying to embarrass you. Just a friendly discussion. I can't hear you. Don't worry. Interfaces I was mentioning to you is a mechanism by which we can transfer the data. As I mentioned to you earlier, in a fluid simulation, the unknowns are pressure, 3 components of velocity, density and temperature. In this case, we are talking about pressure and 3 components of velocity. So by rotating, we have computed P, U, V and W. But the stationary part, how will it know what are the values here? So what happens is we have interface. So this interface completely transfers all the values to this interface. Because these two are same in geometry, values can be transferred across at every time instant very, very easily. So now you know what are the values on this lower one, and then it can be computed downside. Okay, otherwise you cannot use the same equation for rotating and the stationary part, you cannot solve it. Okay, so this is the mechanism done, and this is the most tricky part in the rotating CFD simulations, having proper interfaces, because most of the fluid handling equipment have some part of turbines, engines, we have rotations. So how do we model those rotations? That is very, very important, and that is done through interface, proper selection of the interface. Okay. So we are naming it interface 321, and this is also here wall. Okay. Here also the inner part is rotating, outer part is stationary, so we have to create an interface here as well. This is the interface that is created on the side, so bottom and on the sides. Then we hide it, then are now above it, which is this part. So you can see this is interface 231. This was 321. 221 is exact opposite of this. Okay, so this interface is same as this interface. So this interface will transfer all the values to the 321. Okay, so this is the interface 2332. And again, this interface, the side interface from the rotor part, is a complementary interface of this part, that the values can be transferred across. And then there is an interface at the top, rotation taking place, an interface there on the cylinder and on the lower part of the rotation. And then we can create blade selections. We can identify them as blades, and this was the cylinder interface that I was talking about, opposite to this one. This is the interface on the cylinder opposite to the other one. So this way, around it. So we have created 3 interfaces. All the surfaces we have named. in CFD, if you don't name a surface, it automatically takes as a wall. Although you will not know which surface that is, it's better to give some name. But suppose you don't give a surface a name, it by default takes it as a wall. So make sure all the moving surfaces are named. If you have forgotten to give any stationary surface, it will give it a name as wall. Okay, and then mesh generation. We have given some sizing functions. Again, as I mentioned to you, finer the mesh, better the results will be, and but finer the mesh, more computing power you will need. So I have developed a strategy here. I have given some values here, and if we give those values, the mesh will be formed like this. So you have this mesh formation where injection takes place from the top here, and the flow takes place injection takes place from the top, flow takes place all around it, goes from here and comes out from here. So this is how the injection the flow will take place in this. So we can close the mesh, and now this is the Fluent solver part where we can select the models, and where some difference is there as compared to our earlier discussion, because I'll be running DPM, discrete phase model, now alongside CFD to see how the particles are spreading. Keep in mind, this simulation or similar to this simulation you can do for tracking motion of any injected particle, okay, on the flow stream. So you can have, this is an example of an inhaler, but you can have many other applications where you inject second phase and see how fast it is spreading in the flow domain. Okay, so this is also you can do. Right, so I have opened the Fluent. I'm putting gravity here at 9.81 meter per second square, because the particles have weight, the gravity influences their motion, so I'm putting gravity there. The initial motion is steady, we're not running transient, we're running steady state motion. And then the length units have been changed to millimeters, angular velocity has been changed to revolutions per minute. We are running model viscous laminar, and in this case there may be possibility of turbulence, so we are using k omega turbulence model. You can use other turbulence models as well, but in this particular case k omega works reasonably well. So, but if you wish, you can use other models as well. And select the options as shown and click OK. So we selected it. Then the rotation part, this is rotating in the clockwise manner, so we put y equal to -1 as the axis rotation, and we specified rotational velocity as 2000 rpm for the inner part, inner blade, 2000 rpm, and the axis about it rotates is y, and the value is 2000 rpm here. Then we do is we combine the two interfaces, like the like and like interfaces need to be combined. Fluent automatically does it, but sometimes it does it in a very wrong manner. So you need to check it, the interfaces, that you are connecting the proper interfaces from one side to the other. If you connect it wrongly, solutions will be wrong. So bottom with the bottom, side with the side, cylinder with the cylinder. So whatever name you have given, the name should sound similar. You can select it. So like for example here, you can create mesh interface, interface zone side 1, interface zone side 2. These two should be same interfaces, like 2 3 3 2, 1 2 2 1, and then you can create the interface using the create button. If it has created some wrong interfaces, you can delete it. Like in this particular case, it has created some wrong interfaces which I have deleted. So make sure that the interfaces it creates are the proper one. Fluent tries to do it automatically, but as usual, softwares can make mistakes. So check it, create interfaces. So like here again, proper interfaces are being created. So 3 interfaces have been created. and then we go to blades, and for blades I am putting them as a moving wall because blades are moving at the same velocity along the x axis, and we are applying slip conditions to be no slip conditions, so this is not slipping with respect to the moving flow, this is moving with the flow, and this value I have given here, so this is for blades. And then we have copied the boundary conditions of blades to the entire moving part, that is the cyclone part, and so this way we have given the boundary conditions to it. Then we go to inlet, and an inlet I have given 0.5 meter per second as the inlet velocity, as I discussed earlier. Inlet 2, 0.5 meters per second velocity. Outlet, we are giving 0 gauge pressure. So as I mentioned to you, outlet is 0 gauge pressure, inlet 0.5 meters per second. Rotation part I have given the speed of rotation. So this is fully resolved now. The solution method, nothing much to do. Only thing we are doing second order upwind scheme, which is more accurate. Then we initialize the values, and as we have done earlier, we initialize from inlet. Try not to have 0 velocities at the initialization, and then we can run this simulation. So after 500 simulations or so, we will see that it is starting to converge. So now what we have is, we have Eulerian model of the airflow through the inhaler. Okay, so we have pressure, 3 components of velocity through inhaler, but what we don't have is the motion of the particles. So how do we do that? Keep in mind, this is the steady state model. So we have just done the moving reference frame. I haven't done the sliding mesh, MRF. Now, if we go back to model, we see that this discrete phase is off. Discrete phase model is off. So now in this case, we click on this and we switch it on, the discrete phase model. You can see here, lots of things can be done here. Electric potential, acoustics, solidification and melting, heat exchangers. So many things you can do within this, separate models for that are available. So what we are doing here is, we are using discrete phase model to model as the particles move in the system. Here I have taken some selections which are more appropriate for the practical use. So number of continuous phase iterations per DPM iteration 10. So for each DPM iteration, it will run 10 iterations of the airflow. So it is running 2 simultaneously, DPM iteration, then 10 iterations of the flow, so that PUVW can be modeled. Then the maximum number of steps 50,000. This is just to demonstrate length factor, that is fine. We are using Safman lift force. All these forces can be used in the modeling process, and there is a detailed explanation for everything. Like here we can have collision, if particles are colliding, that can be modeled. It can be stochastic collision, breakup of particles, erosion, accretion, all these things can be carried out here. I am doing a simple model here, so I am just considering the lift force, Safman lift force model, but you can choose any of these. Suppose you are having a material that while coming out strikes and gets eroded or gets deposited, so you can run all those models here, erosion, accretion. So with time, these things are becoming more and more sophisticated. Sometimes empirical models are used which are embedded in CFD, and that can be used for the calculation. Okay. Then we go to injection surface and we go to create and edit, and at the injection surface we give these dimensions. So at the injection here, then we give the diameter of 0.0032 meters. This is the diameter of the particles coming from injection, and we can define the velocity magnitude here. I am giving 5, we can change it to 10, 11, depending upon at what velocity solid particles are coming in, and then this gives you total flow rate. And we have different options of different injection options which are quite involved. I will not go into that at this moment. Just to mention to you, you can select the diameter here and then particles will be injected from there. You can give density of the particle. So depending upon the material, which is sub-beta ml, we know the particle, the density of that is given here. The material type is inert particle. So we are not taking any reactions into account, although in some cases you can. In this case we are just putting this and we can create the DPM model working now. So this is how DPM model is working. Now we need to give some momentum momentum boundary conditions at the injection phase. So we are giving the turbulence values at the inlet phase. We are giving the velocity magnitudes, very small velocities at the injection phase because it's almost stationary. So I'm giving very small velocity at the injection phase. It has to be given non-zero to simulate the actual real condition. In actual case, there is no velocity at the inlet phase. Air is not moving. Air is only coming from the sides. Okay, only solid particles are being dumped down. So I have given velocities of solid particles, but if I give air velocity to be zero, simulation will not run. So what I have done is I have given very small velocity there at the injection of 0.01 meters per second. It is a non-physical reality. Okay, sorry, what is the non-physical? It is non-physical in the sense it just gives you some motion there, but that may not have any effect on the motion of the particles downstairs. But it will allow simulations to run. So it will have only influence in the inlet region. So these are the injection velocity boundary conditions or momentum boundary conditions. And then we are selecting the residuals for the monitors for the pressure and momentum or continuity and momentum, and then we allow iterations to take place. So this is the simple model of the inhaler running with moving reference frame and the DPM model. This is the first part of this, and this is only carried out to make it stable. If you run transient to start with, it will not become stable. So whenever you are running any transient simulation, it is advisable that you first run it under a steady state condition. Bring your residuals down as much as possible. If you bring residuals down and use this as the initial condition for your transient, you will have much higher chances of convergence later, because otherwise you find the very fine mesh, everything is okay, but your system is not converging. You are getting some overflow error and all that. This is the main reason. So first use simple simulation, bring residuals down, and then run the complicated simulations from that particular point onwards. Okay? Any questions, please? So this part is done. Now what we are doing is we are running the transient part, that is the real, how actually it works in reality. So we go to general and select transient here. Select transient here. Keep in mind gravity is already selected, because that means motion of the particle. Particles have mass and they have inertia, so we have taken gravity into account. Now here we have to give some values. So on the discrete phase is unsteady now, so we have to give unsteady particle tracking and track with fluid flow time step. So we are tracking the flow particle alongside the fluid flow time step, and particle time step size is 0.001 second. So 1 millisecond I am tracking particle every millisecond as they travel in the flow. The maximum number of steps is 500, and this is a length factor of 5, and number of continuous phase interactions per DPM iteration is 5. So for one iteration of the particle, we have 5 iterations of the flow. Okay, 5 iterations of the main flow. Earlier we had it 10, but for transient we are. And the start time I am taking at 0.01 second and stop time is 0.06 second. In between these 0.01 to 0.06 seconds, we will see how the motion is. The particle is salbutamol that I have discussed earlier. And in this case, we are trying to specify the flow in the cyclone separator. So we go to cell zone conditions, we go to cyclone separator, and we say that cyclone separator is moving with mesh. Okay, earlier we had steady state motion, we gave rotation, but now we are moving the mesh alongside the motion of the blade. So we are giving the cyclone separator the mesh motion, and again the value is -1 and 2000 rpm. So mesh is rotating at the same speed as the blade. We change the under relaxation factor for convergence or more stable result. Momentum especially very small, we are getting momentum conditions. For kinetic energy and dissipation rate it is 0.5, for pressure it is 0.5. Now I mentioned to you what under relaxation factor do is, suppose I have done the calculations at this particular point, so I got these results. I put these values in my equation, I get this result. So should I go from here to next? So what we do is we say no, that is dangerous, because if you go from here to here it may become unstable. So we say okay, let's take difference of these two times 0.1 and add that to this. So in place of jumping from here to here in solution, we're saying let's go here, take a step slowly. Don't go from here because then it may go outside, it may become unstable. So by managing the under relaxation factors here, you suppress the oscillations. Okay, you slowly move in the correct direction. In place of you have seen sometimes situation become out of control, isn't it? And we say take a deep breath and it will be all right. So what we do is we're taking deep breaths. We're instead of jumping from here to here to here, saying okay, let's take one step at a time slowly, and then things will become stable. So that's why the word relaxation, isn't it, Nitin? You become more relaxed slowly under relaxation. Okay. So after this, then there are so many things for saving files every 5 minutes. Then we can create solution animations, and there are so many peripheral things that you can do to see how the flow is taking place. So we can create animation, we can create animation sequence, and we can give particle variable, particle velocity magnitude for salbutamol, and then we can draw it on the visually see the flow is taking place inside. So once we have given the particle properties, and now we can start calculations, and in the calculations we have to give time step size, number of time steps, and maximum iteration per time step. Is very important for transient. So every 0.0004 seconds the calculations are being carried out. Total calculations are 144. So total time needed for this is 144 times 0.004. That comes out to be 0.06 seconds. So it is calculating from 0.01 to 0.006 seconds. So this is how we run the simulations of the CFD, and then we have got some results from this, but this is how the simulations are run. Do you have any questions on this? Is general outline clear? Creating geometry, 3 parts, inlet, outlet, interface, create mesh, boundary conditions at inlet and outlet, rotation of the central part, steady state run, go to DPM, run it, go to transient motion, again dPm, and you get this type of results. So next stage is how do we post-process the results. So here what we have done is I have created some planes on which motion can be shown. So here if you just go to the view, XY plane view, and go to plane and check align with the plane and it specifies 0, 0, 0, you can create a plane going through the center of the inhaler, just through the center of inhaler. And then on that plane you can show velocity, pressure, anything. So this plane is created at 0, 0, 0. Keep in mind our central axis was 0, 0, 0. So plane that you create on that will be going through center point. So that is 0, 0, 0 plane, and on that plane you can see the variation of static pressure. So see here, because of rotation, static pressure is a lot higher on the rotation part because centrifugal. Okay, less part there is very little pressure difference. Although flow is coming down from this, the higher pressure is on the inlet pipe. So can we model the inlet section such that pressure is more uniform across this? That is one type of the analysis that you can carry out. Okay. Now again here this is slightly higher pressure and slightly lower pressure because flow takes place in the downward direction. So flow is coming from here, high pressure goes down here, low pressure. We would like to have this difference reasonable, difference between this and this, so that flow can go in the downward direction. Then what I have done is I have created a line through the center of the inhaler. So again if you go to the post processing create and go to line and give these coordinates for line x, z0 on xz plane. Okay, y is varying from 13.5 to minus 43.962 and minus 43.692 to minus 54.1. In this case x is also varying. Okay, so you get a straight line, then you get an inclined line going through the outer duct. So you can create a line like this, and you can now I would like to just put some numbers to it. You can get simulations done, but if you cannot explain, you'll be having difficulty getting the desired result as far as a master's PhD or anything else is concerned. So what we are doing here is we are plotting variation of coefficient of pressure through that line. So how pressure is varying along that line, or at different sections how pressure is increasing or decreasing, because pressure differential is related to flow velocity. Okay, flow rate. Higher the flow rate, higher the pressure differential. But geometry affects the pressure difference as well because losses take place. So how geometry is affecting the flow, it can be seen from this particular figure. So then we go to reports under the graphic section. Surface integrals compute area weighted average of the static pressure on that plane, that is fine. Then we plot it along XY line, and you can see the static pressure remains almost same in the injector and it starts decreasing in the cyclone separator, and the pressure further decreases through the outer duct while recovering at the exit. So this is exit. So pressure has recovered here to some extent. It has decreased here. This is your centrifugal part and this is your inlet. So pressure, it has come from here, this part, here and this part. So here it has recovered here, is continuously losing it here, and then it is recovering on the outer part as well. So this is how the pressure coefficient varies. Similarly, we can see the velocity difference, and as you can see here now, this is very important. You can see high velocity coming through here, but slightly lower velocity coming through here, isn't it? So if your particles are slightly bigger, it may happen that your deposition of particles may take place here, isn't it? It may happen that particles may deposit when you're putting in your mouth because of whatever action take place. So there is a likelihood of deposition here. So particles are not symmetrically coming out here. They're coming out here okay, but from this point onward the trajectory is a bit different. So that you can see how we can do that. by modeling the parameters. So here, just for the sake of quantitative analysis, some things have been calculated. Differential pressure from inlet to the outlet, that is 30.26 pascals. Power needed to rotate, and the efficiency is the power needed to rotate, that is input over output, and we are seeing the power efficiency is about 2.5% in this particular case, and differential pressure is about 30.26 pascals in this particular case. We can see the particle motion here. You can see the animation of the particles as they get along from the top to the bottom using this. You can see how blades are imparting rotational motion to the solid particles. And how the particles are slightly asymmetrically distributed across it. Okay, so this is the basic description of inhaler I wanted to give to you. After this, I'll show you the video of actually how it is made. You can create that, you can have a look at it overview, and in your own time, then if you wish, you have the notes, you can start creating this. Okay. Any one of you doing a PhD project in this, I hope it will be of great help to you. Put the boundary conditions and run it. So it is good for some of you, it may be good for some of your students, some of your friends who can run things like that. And basically here, just by changing the blade shape, you can see the influence on the motion of the particles. Changing the inlet diameter, influence on the motion of the particles, you can calculate that. Okay, so we take a break a bit, and then we'll do the video part.